Now let's take a look at the trigonometric form of a complex number. So as with polar coordinates, the rectangular ordered pair AB can be represented in polar coordinates r, theta. So the location that A, B would point us to in rectangular coordinates, right, we said can also be expressed in polar coordinates r, theta, where r represents the distance the point is from that origin, and theta represents the angle between the positive x-axis and the segment connecting the origin and the point. So that really just means that the point that we're after, we know, is on the terminal side of some angle theta, which is in standard position. Okay, so the only thing new here is we're saying now this is the location of a complex number instead of just some regular old point like we were doing before. So this is just saying, hey, here I have some complex number, but I can still think about the location of that complex number, right? We said there's this correspondence between a plus bi and the location of the point a, b, and that is where the complex number is going to be. And so if we know that location, we can say, well, the distance from the origin, right, to that location we'll call r, and then imagining that point on the terminal side of some angle theta in standard position. So now we can describe the location of this complex number using r and theta. Well, we know that if the rectangular pair AB represents the same point as the polar pair r theta, then we have a relationship, right? A is that x value, so we get A equals r cosine theta. And since B is representing that y value, or the vertical value, right, we have B equals r sine theta. So because of that, if I have some complex number z equals a plus bi, then a can be replaced by r cosine theta. B can be replaced with r sine of theta. And then, but noticing that when I have bi, so I still have this I here, okay? And then I can actually pull out the r, and that leaves me with just cosine theta plus, and since this r is pulled out, sometimes we see the I in front of the sine theta, and so that's okay too. And so we get r times cosine theta plus I sine theta. So in summary, if r is greater than or equal to 0, and the angle is between 0 and 2 pi, the complex number z equals x plus yi. So here we're using x and y just to kind of remind us that we're talking about horizontal and vertical components here, the real and imaginary parts. But this number, same with a plus bi, may be written in the trigonometric form of a complex number as r cosine theta plus r sine theta times I, which is just r times the quantity cosine theta plus I sine theta. So let's look at applying this. So example, complete the table and state the angles in radians between 0 and 2 pi. Round to the nearest hundredth when necessary. So here what I'm given is some numbers that are in the rectangular form of a complex number. So what is the rectangular form? Let's correct this here. So what's the rectangular form? Well, that just means that we have the regular a plus bi or x plus yi. And then the trigonometric form is what we just established. So we just want to kind of keep track of what form do we have and what form are we headed to. So how could I then go find this trigonometric form? Well, this would require me to find r and theta, but I know that I've done that before because I have two relationships that I can use. So let's kind of write them somewhere where we can remember. So we have r squared equals x squared plus y squared. Again, that's just the horizontal and vertical components. So in the case of this complex number, right, it's just going to be the x and the y here because that's what I use to graph them or find their location in the complex plane. And then I know that I also have tangent of theta is y over x. So I'm going to kind of keep those in mind. So in order to understand how to apply those, I really want to just draw a little picture here. And I'm going to get, negative 3 plus 3i. So negative 3 for the real, up 3 for the imaginary axis. So that is going to be the point right there. Okay, so that looks good. And then the angle in standard position that ends right at that segment is going to be theta, and then r is just the length out to that point, and this is negative 3 plus 3i. So because this point, right, negative 3 plus 3i, this complex number corresponds to the point negative 3, 3, I can use the same idea of the r squared plus equals x squared plus y squared. So I'm going to have r squared equals negative 3 squared plus 3 squared. R squared is, 9 and 9 is 18, so r is 3 root 2. So I'm just taking the square root of 18 there. All right, r has to be positive because it's a length. Now let's find theta. Well, what's nice is I can see that this r is really just on this main diagonal going in the second quadrant. So I know, even though I have this idea that tangent of theta equals y over x, I don't need that right here because this is a nice angle on my unit circle that I can see pretty clearly. So this I can say is just theta is 3 pi over 4. Okay, so now I'm ready to put it in this trigonometric form. So I just kind of, copy and paste this idea. So r is 3 root 2, so I just copy that down. And I'm going to leave things exact where I can. So in this case, I have these nice exact values. So I'll just do that. Plus I sine 3 pi over 4. So what I just wrote, I have z equals 3 root 2 times the quantity cosine 3 pi over 4 plus I sine of 3 pi over 4. And there I have my trigonometric form of a complex number. All right, let's try the next one. The next row is z equals 1 plus 2i. So we're going to do the same thing where we have to kind of see what that would look like. So 1 is the real part. So here's my real axis. Here's my imaginary. So over 1 up 2. So 1 plus 2i. But of course we have some length r and the angle theta. So let's solve. So r squared is just 1 squared plus 2 squared. So r squared is 1 and 4 is 5. But remember r equals root 5. So make sure you solve all the way for r. And then tangent of theta is y over x, so 2 over 1. And tangent of theta is 2. So that is not a tangent value that I'm familiar with from the unit circle or something like that. So what I want to do is use tan inverse. Tan inverse of 2 is, so we want to keep these in radians. So first I just go to my my calculator, make sure I'm in radians, and I just did this calculation before, so I'll use this. So tan inverse of 2 is 1.12. Okay, so if it doesn't say rounding to the nearest hundredth, is kind of a good bet here. Okay, so this is radians, just to kind of remind us what we just found. This is an angle, and we know where does tan inverse return angles in quadrant 4 and quadrant 1. And so in this case, this is a quadrant 1 angle, and I'm in quadrant 1 when I drew my complex number. So it must be the right angle, and I can move forward as this being the value of theta. So now I am ready to write this in my trigonometric form. So z is, let's see, first I need my r, root 5 times cosine of 1.12 plus I sine of 1.12. Boom, boom, and I can just keep it like that. Okay. Last one. This is a little easier because now we're just going in this direction. And in order to go from the trigonometric form to the rectangular form, it's literally just as easy as evaluating it. So I'll put that work over here. We have a little more room. So this is just 2 times. Well, what is cosine of 2 pi over 3? Well, that's negative 1/2. And what is, so then I have my I, can't forget the I, sine of 2 pi over 3. Well, that's just root 3 over 2. Okay, and then when this 2 comes in, that gives me negative 1 plus just I root 3. So I'm going to put that over here. Z equals negative 1 plus I root 3. And if you have this as z equals negative 1 plus root 3i, that's okay too.